Revolutionary quantum compass could soon make GPS-free navigation a reality. A milestone in quantum sensing is drawing closer, promising exquisitely accurate, GPS-free navigation. Peel apart a smartphone, fitness tracker or virtual reality headset, and inside you'll find a tiny motion sensor tracking its position and movement. Bigger, more expensive versions of the same technology, about the size of a grapefruit and 1,000 times more accurate, help navigate ships, airplanes and other vehicles with GPS assistance. Now, scientists are attempting to make a motion sensor so precise it could minimize the nation's reliance on global positioning satellites. Until recently, such a sensor, 1,000 times more sensitive than today's navigation-grade devices, would have filled a moving truck. But advancements are dramatically shrinking the size and cost of this technology. For the first time, researchers from Sandia National Laboratories have used silicon photonic microchip components to perform a quantum sensing technique called atom interferometry, an ultra-precise way of measuring acceleration. It is the latest milestone toward developing a kind of quantum compass for navigation when GPS signals are unavailable. GPS-free navigation a matter of national security. Accurate navigation becomes a challenge in real-world scenarios when GPS signals are unavailable, said Sandia scientist Jongmin Lee. In a war zone, these challenges pose national security risks, as electronic warfare units can jam or spoof satellite signals to disrupt troop movements and operations. Quantum sensing offers a solution. By harnessing the principles of quantum mechanics, these advanced sensors provide unparalleled accuracy in measuring acceleration and angular velocity, enabling precise navigation even in GPS-denied areas, Lee said. Silicon device mass-producible and more affordable. Besides size, cost has been a major obstacle to deploying quantum navigation devices. Every atom interferometer needs a laser system, and laser systems need modulators. Just one full-size single-sideband modulator, a commercially available one, is more than $10,000, Lee said. Miniaturizing bulky, expensive components into silicon photonic chips helps drive down these costs. We can make hundreds of modulators on a single 8-inch wafer and even more on a 12-inch wafer, Kodagala said. And since they can be manufactured using the same process as virtually all computer chips, this sophisticated 4-channel component, including additional custom features, can be mass-produced at a much lower cost compared to today's commercial alternatives, enabling the production of quantum inertial measurement units at a reduced cost, Lee said. As the technology gets closer to field deployment, the team is exploring other uses beyond navigation. Researchers are investigating whether it could help locate underground cavities and resources by detecting the tiny changes these make to Earth's gravitational force. They also see potential for the optical components they invented, including the modulator, emitter, quantum computing, and optical communications. I think it's really exciting, Kodagala said. We're making a lot of progress in miniaturization for a lot of different applications. Quote. Multidisciplinary team lifting quantum compass concept to reality. Lee and Kodagala represent two halves of a multidisciplinary team. One half, including Lee, consists of experts in quantum mechanics and atomic physics. The other half, like Kodagala, are specialists in silicon photonics. Think of a microchip, but instead of electricity running through its circuits, there are beams of light. These teams collaborate at Sandia's Microsystems Engineering, Science and Applications Complex, where researchers design, produce, and test chips for national security applications. We have colleagues that we can go down the hall and talk to about this and figure out how to solve these key problems for this technology to get it out into the field, said Peter Schwint, a quantum sensing scientist at Sandia. The team's grand plan, to turn atom interferometers into a compact quantum compass, bridges the gap between basic research at academic institutions and commercial development at tech companies. An atom interferometer is a proven technology that could be an excellent tool for GPS-denied navigation. Sandia's ongoing efforts aim to make it more stable, fieldable, and commercially viable. The National Security Photonics Center collaborates with industry, small businesses, academia, and government agencies to develop new technologies and help launch new products. Sandia has hundreds of issued patents and dozens more in prosecution that support its mission. I have a passion around seeing these technologies move into real applications, Schwint said.